here are the rest of the notes. So now we're going to look at number 6. So on this one, they told me x minus 3 is a factor. So how did they figure out that x minus 3 is a factor? They probably graphed it. And they probably saw that 3 was an x-intercept. So x minus 3 would have to be a factor. Now, we don't know how to factor this the rest of the way because if it's an x to the cube, so we will divide it out to see if we can make it something smaller. If you were to graph it, you would see that these last two would be in-betweeners as well. So it's going to probably be a square root type thing. You can see them, so they'll be square roots. So you got to find those last ones. So we're going to put 3 in the box. And then you get 1, 3, negative 12, and negative 18. You drop the 1 and you have your party. You multiply, you add, you multiply, you add, you multiply, and there's that remainder 0 that we needed. So this is the remainder, number x squared. We get that x squared plus 6x plus 6 times x minus 3 will get this. This does not factor further. So our factored form over the integers is x minus 3 times x squared plus 6x plus 6. But I want to find all the roots. So I have 3. Where are my last 2 roots? Well, I can get that from solving this guy. You can do quadratic formula, which would be a really good thing to do. Or you could do complete the square, which is what I'm going to do because that 6 is even and it's easy for me to cut in half. X plus 3 squared is the closest thing it is to, which is a 9. Okay, but I need to get to 6, so I'm going to subtract 3. Okay, so the guy that's left is this. I can solve that by adding the 3, and I get x plus 3 squared equals 3. Square root both sides. Don't forget your plus or minus. X plus 3 equals plus or minus the square root of 3, and then you would subtract 3 to get the last 2. So negative 3 plus square root of 3 and negative 3 minus square root of 3. So those two are the last roots. Okay, now this one is interesting for a couple reasons. I would not divide to find this one. First of all, I do know some things about this personally. If you graph this x to the 4th minus 16, it's just going to be a quartic curve. Downshifted 16. Okay, so I see 2 of them. 2 of the roots are 2 and negative 2. I can double check to make sure I'm right by looking at the table. And I am. Now, where are the other 2? Well, you might not be sure unless you know stuff about this graph that you have it all. If you go to zoom 0, which is zoom fit, oops, sorry. I messed that up. I don't even know what to do. Look, I just screwed it all up. Oh. They don't even let me turn it off. Miss Bruno done messed it up. Okay, I'm sorry. Anyway, if you are to graph it, are you kidding? And that's the zoom fit. You can see that it's a U-shaped curve. You can adjust your window a little bit and maybe go down. Let's go down like to negative 30. I still can't see it. I think it's because the Y max is so big. Yeah, because it will just be below it. They're making sure you see that that's all the curve right there. Okay, so we do see the whole picture. So we have 2 and negative 2. How do you get the last 2? Well, what I would do is I notice that this factors right away. That's x squared minus 4, x squared plus 4, because that's the difference of 2 squares. X squared minus 4 is x minus 2x plus 2. And then x squared plus 4 is the last ones. This is factored form. There's the 2 and the negative 2. Where can I get the last ones? That's from solving this guy. They should be imaginary because I can't see them. And I know they're there because I'm looking for 4. And when I solve this, I take the square root of both sides. I get plus or minus 2i. So the last two are imaginary, and 2i and negative 2i. Okay, just one more of these. And then they're going to make a little table for you. Okay, now on 8, it's important because if x minus 2i is a factor, you have to know immediately, because they only come in pairs, that x plus 2i is also a factor. So you have 2i and negative 2i, and I'm only looking for 3. Probably the easiest thing for you to do here would be to graph it and find that last one, because it has to be real. The last one will have to be real because if 2 are imaginary and you're looking for 3, 1's going to have to be real. Plus, it's an x to the third. There's no way to draw a snake baby without passing through the x-intercept. You have to have at least one real one. So you can go to your calculator and find it that way. The other thing you could do is you could say, okay, this is not how we usually write factors. If you multiply these two together, you get x squared plus 2ix minus 2ix. Those cancel out. Minus 4i squared, which becomes x squared plus 4. That means one of the factors is x squared plus 4. So to find the last one, you would have to do long division. You would have to do long division. You could long divide it out. Some of you decided you don't like that very much, though, because you have to put a 0x in here for sure. So then maybe you did go to your calculator. If you went to your calculator, x to the third minus x squared plus 4x minus 4. And I graph it. Oh, my graph's a little messed up here. Zoom 6. Go back to that normal zoom if we can. Okay, yeah. So the wiggle around here usually tells you there's an imaginary. It looks like it's at 1. If I go to the table, I can confirm that it is at 1. You could do second calculate 0. 1 is the last root, which means that x minus 1 is the last factor. If you divide this out, you'd also get x minus 1. Is it possible for polynomials to have only one imaginary roots? No. They always come in conjugate pairs. They always come in conjugate pairs because they come from the quadratic formula or square rooting both sides and the square root of a negative. Okay, and then the last thing they want you to know is kind of what we were talking about right here, how there had to be 2 because they come in pairs. There is a chart you can make, and I actually put it in the notes if you just want to copy it off there, telling you what types of functions have what kind of roots. A linear has 1, 0, and it has to be real because it has to cross the x-intercept. Quadratic, we talked about earlier this year, they have 2 zeros. They could both be real. You could have 1 real with multiplicity 2. You could have 2 imaginary. Those are your only choices. Cubics have degree 3. You could have 3 real. You could have 1 real and 2 imaginary. You can have 1 real with multiplicity 3. You could have 2 unique reals, but one of them have multiplicity 2. And quartic has lots of different possibilities. I don't have enough room to write this down right here. But you could have 4 reals. You could have 1 real, multiplicity 4, 1 real with multiplicity 3, and a regular real, like 2 reals and 2 imaginaries. There's all sorts of things if you want to look at that chart. Okay, that's it. Tomorrow we will do the worksheet that goes with this.